Hi students, this is lecture 5. It's about network modeling. In the previous lecture, we discussed simulation in general, and we put the pillars of network simulation. From now on, from lecture 5 to lecture 8 or 9, we will discuss now network simulation specifically. A typical network simulator can provide the engineer or the programmer with the abstraction of multiple threads of control on inter-thread communication. Functions and protocols are described by either a finite state machine or native programming code, or a combination of both. Simulator typically comes with a set of predefined modules and user-friendly GUI or GUI. Some network simulators even provide extensive support for visualization and animation. There are many types of network simulation packages. Some has GUI, some doesn't have GUI. Some produce data and you have to print or plot these data using other third-party graphing tools like Excel or spreadsheet. Some has like everything. It has GUI, it has visualization, and some has reporting tools to make a simple report of your simulation. Basically, network simulation, it's about like it contains of many native programming code like C, C++, and these blocks of coding usually they are abstracted in functions, and the simulation actually is how to integrate these functions together to implement a real system by using finite state machine. Simulation of networks. Simulation of a network frequently requires a collection of interdependent, nested, concurrent sub-simulation arising from. It means that you have to build components and simulate them, then use these components together to simulate a bigger network or a wider range of network. The entities that are the nodes of the network and the processes therein. For example, in network we have routers, we have switches, we have links, we have everything. Each of these entities, they have its own package. You have to simulate these entities alone. Then after you are successful of simulating these entities each aside, you will combine them to make network simulation. The links that are the edges of the network and the processes therein. Plus to the entities, you have to configure the links so it will be compatible for using entities among them. In the specific case of computer communication networks, these elementary subcomponents span functionally distinct elements of the system such as networks, links, circuits, and the propagation medium, etc. The propagation medium is like if it's Wi-Fi, if it's like wired channel, optic fiber, etc. In practice, simulation of these elementary subcomponents can be conducted using different approaches, with certain approaches being better suited to the certain components. A broad classification of approaches would include discrete event-driven simulations. This is a famous simulation, so there are many simulators that follows discrete event-driven simulations. Some simulators follows time-driven simulations. Some are based on algorithm simulations. Some are based on circuit simulations. Some are based on physical media simulations. Different simulation tools specialize in one or more of these simulation approaches. For example, NS2 and OpenNet. Now, NS2 is becoming obsolete these days. A new version of NS3 has become prominent, and people are using NS3 a lot these days. But they have the same basic idea that they are top of each other. NS2 and OpenNet deal primarily with event-driven simulation. Like their simulation depends on events. We defined event as like a point in time previously, while SPW, COSAP, and Simulink MATLAB focus on time-driven simulation. Texas Instrument Code Composer provides a platform for algorithm simulation. This is another type of simulators. While ANSI VHDL Verilog and Sirocco support circuit simulations. These are hardware simulators. Like instead of building ICs, you simulate these hardware using very high definition language via Verilog and VDC instead of using the hardware itself. Now advanced FPGAs use these, they are compatible with VHD and Verilog. Instead of printing out integrated circuits, you have to program them first, then compile these two programs into direct hardware components, which are they based on circuit simulations. On the other hand, PSpice, ADS, and XFDDT are often used for simulation of radio frequency channels and other media. So we have various types of simulations. In networks, we are dealing with many things. We are dealing with physical media, we are dealing with algorithms, we are dealing with time-driven, with discrete events, and even circuits. So in this course, in the lab, you're supposed to have to learn how to use OpenNet in doing simple network simulations. We are going to have an assignment in the future. Each student will implement certain network topology type on a specific simulator. I will choose the simulator later. OpenNet is a little bit difficult to use, and for students they have to learn properly in the lab to do so. So we are not going to use OpenNet in this scenario. Okay. This figure actually explains how network simulations can be encompassed by very different simulators. This example hierarchy for a case of computer communication network is depicted in this figure. For example, in networks such as in event-driven simulations, NS3 or OpenNet or NS2, they deal with networks, entities, and links. So the data types in these simulations are usually packets, messages, or flows, like data stream flows. In links, the main data type is waveforms. So waveforms usually is based on time-driven simulations, just like MATLAB Simulink. If you are familiar with MATLAB, you may have seen some waveform generation of MATLAB. Now on the bottom layer, which is the hardware, there are some DSP algorithms, circuits, and medium, like physical media. For the integrated circuits is design of the integrated circuit itself, we use VHDL Verilog. For DSP, we use algorithm simulation for DSPs, like Texas Instrument Code Composer. The network modeling and simulation process has many steps. The figure shows successive refinements of a block diagram describing the typical phases in the modeling and simulation process. Within this, block number 1 represents determination of actual system to be modeled and simulated. Block 2 and 3 constitute modeling. Let's see here, physical system, existing or proposed. In the second block, conceptual modeling of the physical system. And the third step or block, after we had our modeling, we will have our mathematical modeling of the component of conceptual model. So each block is dependent on the previous block, as you can see. For block 4 and block 5 constitute model in implementation in computational terms and instantiation where via input parameters selection. After you have your mathematical model, you can implement discretization and algorithm selection for the mathematical model. Let's use this mathematical model. For block 5, you will use computer program of this discrete model. You have your algorithm. If you have your algorithm, you will easily implement it on computing program. Block 6 represents the actual simulation execution, while block 7 represents the analysis of the simulation, data generated on performance measures through simulation. So after you have your program successfully, you can make your numerical solution of the computer program model. Then you can get your results and represent your results by reporting in block 7. This is the main idea of any simulation you have. So if you want to make a simulation, you have to start from the physical system. After the physical system, you will draw the conceptual modeling. From the conceptual modeling, you will design, you could propose your mathematical model. After mathematical model, you will make your algorithm selection, then code this algorithm using computer any programming language, then collect the results of this computer program language, then represent the results as simulation solution or numerical solution. Developing models. The models process in block 2 and 3 frequently requires making simplifying assumptions and introducing approximations to reduce the model's complexity. Before we said that in terms of simulation, we cannot encompass every aspect of a physical system. We have to choose the most important parts of the system that we can model, and we can find a mathematical model for it. Some systems they cannot be represented by simple mathematical models. So in order to do block 1, block 2, 3, we have to do some approximations to reduce the models of complexity. This simplification can be carried out by two distinctive levels. First, by modeling. Here we simplify the functional distribution of the network elements. For example, we may consider packet transmission to be error-free, or we may consider the channel contention due to simultaneous radio frequency transmission is negligible. Such simplifications themselves generally fall into one of the three categories. The second distinct level is performance evaluation. Here we simplify the measurements being made to the simulation to provide less precise but potentially more useful estimates of the system's behavior. So you have two choices. Either you neglect some unimportant or negligible factors of modeling, or you can ignore some curves or unwanted behavior in your results. So you have two choices to make your system less, to reduce your system complexity, either by reducing the modeling, simplifying the modeling, and simplifying or reducing the performance evaluation. In modeling, we have three different categories to do so. The first one is system modeling. Simplifications at the highest level of description of the interactions between the distinct elements. I mean by distinct that are different from each other, are unique, of the simulation. Complexity reduction. As an example, assume that we are simulating a vehicular network, and we choose to assume that the nodes only move in Cartesian lattice. It means that, if you are going to simulate a vehicular network, vehicles, they have irregular shape in their routes. So to simplify the simulation, you will think that, okay, if all vehicles their routes are in Cartesian lattice. It means that in the straight lines. Like, for example, the vehicle starts from point A and goes to point B like this, and point C like this, and point D like this. There are no curves or some irregular shaped roads, because it makes the system more complex. But as a result, this simplification will not affect your results very much. The second category in modeling simplification is element device modeling. Simplifications are the level of description of the behavior within a single element of the simulation. Assume we are simulating a routing protocol, for example, and we choose to assume that each constituent switch is either fully functional or else fails completely, i.e. there are no partial failures. Okay, so when you are going to simulate your element device, such as router or a switch, you will assume these entities, they work 100% fine, and or they will fail or shut down completely. You will not think that, okay, the router may work from one interface and the other interface is not working, which usually happens in real world, but we are going to eliminate this option from our simulation. Okay. The third modeling option, simplification option, is system models and element versus device models. Okay. These are frequently expressed with the reference to the random processes. For example, a network of computers might be connected using links that are drawn uniformly at random from the set of all distinct pairs of nodes. Frequently, simplification of such system and device element models entails simplification in the distribution referenced by their constituent random processes. This brings to us a third type of simplification called random process models. In this simplification, we are going to exploit or make use of randomness, random processes that will make things work properly. Because if you make your, as we said before, if you make your random input, you will achieve fairness of your system models. So instead of trying every type of input, for example, every device, your randomness will guarantee that your system will work at any measure. This is what we mean by the third category of modeling simplification.